The last extension to simply typed lambda calculus is fixed point construct for implementing recursive functions. So first of all, this fixed point construct is not the same one as fixed point combinator that we developed in untyped lambda calculus. In untyped lambda calculus, we have this fixed point combinator, which is simply a very complicated lambda abstraction. So it's a valid expression or valid lambda abstraction in untyped lambda calculus. In contrast, this fixed point construct, not combinator, this fixed point construct in untyped simply typed lambda calculus is a primitive construct. So it is a part of the language definition. So you cannot simulate, for example, this fixed point construct using lambda abstractions. So that's the difference between fixed point construct, which is a primitive construct. So it cannot be simulated with existing language constructs, and fixed point combinator, which is simply an example, a valid expression in untyped lambda calculus. So this is the syntax for fixed point construct. Expression E now has this fixed point construct of this form. And the intended meaning of this fixed point construct is this fix x a dot e is going to find a fixed point of this lambda abstraction, lambda x a dot e. So perhaps this expression E also has a type A. So the whole lambda abstraction is going to have a type A arrow A. Then this fixed point of this lambda abstraction or this function is going to have a type A. So remember that, for example, fx is 2 minus x. We can think of this function as having type integer arrow integer, and f1 is 1, so 1 is a fixed point of type int. So similarly here, this expression E is going to have a type A, so the whole lambda abstraction has a type A arrow A, so therefore its fixed point is going to have a type A. And this observation gives rise to a typing rule for this fixed point construct. So here's a typing rule for fixed point construct. So we want to verify that this expression E has a type A, but inside expression E, we may use this variable x. So we'd like it to confirm that expression E has the same type A, this one, with this type binding x is a type A. So this is the typing rule for fixed point construct. Then what about the reduction rule? So this is the syntax, and this is the typing rule. Now what is the reduction rule? So let's further analyze this informal definition of this fixed point for this lambda abstraction. So this fixed point construct is intended as a fixed point of this lambda abstraction. So therefore, we have this lambda abstraction of type A arrow A, and suppose that it has its fixed point. Let's assume this fixed point. Then from the very definition of a fixed point, we are going to have this informal equality. That's the notion of fixed point construct. Now, this fixed point construct is intended as a fixed point of this lambda abstraction. So we can just so we can substitute this one over here, and then we will get it back again. So let's write it here. Let's substitute fixed point construct here. Then we will have some, informally speaking, some kind of equality. Now, what happens when we reduce this expression using beta reduction? This one reduces to expression E, where variable x has been replaced with its argument, namely the fixed point construct. So now we have some equality between this fixed point construct and this one. Remember that this is not formal notion of equality. It is some informal notion of equality that we will not give a precise definition of. All we are saying here is this one is closely related to this expression. And this observation gives us a reduction rule for fixed point construct. So fixed point construct x a dot e, this one is going to reduce to this expression over here. So this is the reduction rule for fixed point construct. Now we have the syntax for fixed point construct. We have typing rule for fixed point construct. Finally, we have the reduction rule for fixed point construct. Let's see an example. Let's see a typical use of fixed point construct in programming languages. Usually, we use this fixed point construct to define recursive functions, in particular under call by value reduction strategy. So, we'd like to define a recursive function f of type a arrow b such that its argument x is of type a, and this is the body of the recursive function. So this is the typical use of fixed point construct when we try to define recursive functions. Here, we are trying to define recursive function f of type a arrow b, and the formal argument is x of type a, and this is the body of the recursive function. Then according to the reduction rule here, what happens to this fixed point construct? We make a copy of this one, lambda xa dot e, and we make a copy of this one here, and similarly, we make a copy of this lambda abstraction here, and substitute the whole fixed point construct for this variable x. So we substitute the whole fixed point construct for this variable f. And usually we can move this substitution inside this body of this lambda abstraction. So in the end, we have lambda abstraction A, where this function f is replaced with the entire fixed point construct. Now it appears like the recursive functions, this recursive function f is working okay. We have this lambda abstraction, so it's a function, and every time you use this function f, you just replace the function f with the entire definition of the recursive function itself. So you basically unroll this recursive call. So this is the typical use of a fixed point construct when defining recursive function f.